Welcome to a screencast for the rest of the material that we didn't get to during the Monday, November 9th class. These are the last couple examples on the handout from that date that we didn't cover during class. And the first one deals with the bubble of flammable gas that was demonstrated at the end of class. Some data is given for the bubble, and we are asked to find the density of the bubble, the molar mass of the flammable gas, and the volume of carbon dioxide produced when the bubble burned. And let's take these one at a time. First of all, the density of the gas bubble. And of course, density is a mass to volume ratio. The mass of the bubble is given 0.174 grams. The volume of the bubble is also given 280 milliliters, and when we do this mass to volume ratio, what we find is we get 6.21 times 10 to the minus fourth grams per milliliter for the density. Now notice this is a very small density, probably to be expected if we're dealing with a gas. It would have a much smaller density than the liquids or solids we've dealt with so far in this class. And then also note, density can be in different units, and sometimes we might do something like note that if we do the mass in grams, and let's say we do the volume in liters, so 280 milliliters is 0.280 liters, and that works out to be a density of 0.621 grams per liter, and perhaps that's a little more understandable scale-wise. You can imagine a volume of a liter, and then the gas in that volume, this gas would only have a mass of 0.621 grams. Okay, the second part of this question is to find the molar mass of the flammable gas. And what we'll keep in mind, of course, is that molar mass, our goal, is grams per mole. So number of grams that correspond to a number of moles. And in this case, the number of grams are given in the problem. We know how many grams we have. So that means what the problem reduces to is we need to find the number of moles, and then it should be a fairly straightforward plug our values in and get our answer. So how do we find number of moles? Well, since we're dealing with a gas, the ideal gas law is assumed to be followed. PV equals nRT. Number of moles is N. So if we take this equation, divide both sides of it by RT, we get N equals P times V over R times T. And now we'll start putting values in. The pressure is 0.951 atmospheres. The volume, in anticipation of the value for the gas constant R we use, will convert the volume into units of liters, so 0.280 liters. And the value of the gas constant we'll use, since we have pressure in atmospheres and volume in liters, is 0.08206 liter atmospheres per mole Kelvin. And then the temperature will of course have to be in Kelvin, so we'll have to add 273.2 to the Celsius temperature, which gives us 298.2 Kelvin. And if we check our units, atmospheres cancel, liters cancel, Kelvin cancels, and it leaves us with 1 over moles, which will end up being moles. And what we get from this calculation is 0.0109 moles of our gas. And so now to find molar mass, which is grams per mole, we have 0.174 grams of gas. That corresponds to 0.0109 moles of gas. and that works out to be about 16.0 grams per mole. And as usual, determining molar mass can help us potentially determine what the substance is, and it turns out that the flammable gas we are dealing with here is in fact methane CH4, which has a molar mass of 16 grams per mole. Okay, next, what volume of carbon dioxide is produced at 0.951 atmospheres and 25 degrees Celsius? And of course, first of all, we should consider the reaction that takes place, and methane gas CH4 reacts with oxygen gas, and if it combusts, it makes carbon dioxide and water. And the water initially is a gas, and if we let it cool down, it'll turn into a liquid. And of course, we would need to balance this equation to accurately describe what's going on. And now, to get the volume of CO2 produced, what we note is 1 mole of CH4, methane, our flammable gas, produces 1 mole of CO2 because of the stoichiometry of this reaction. So, since we determined in the previous problem that we had 0.0109 moles of CH4, then since 1 mole of CH4 produces 1 mole of CO2, then 0.0109 moles of CO2 would be produced. And as usual, when we do stoichiometry of a reaction, we have to deal with moles. Okay? Now, this is particularly easy. Stoichiometry is 1-to-1. But now we also have to remember that the question asks for volume. And so since we're trying to find volume, the ideal gas law, of course, has volume in it. PV equals nRT. We're interested in volume. So volume will be nRT divided by P. And in this case, volume of CO2 will be 0.0109 moles of CO2. Gas constant, 0.08206 liter atmospheres per mole Kelvin. Temperature of 298.2 Kelvin. And a pressure of 0.951 atmospheres. And moles cancel, atmospheres cancel, Kelvin cancel, leaving us with liters, and this works out to be 0.280 liters. Interesting. That sounds familiar. That's the same volume, 280 milliliters is 0.280 liters, as the bubble. And notice something that's kind of important and potentially time-saving is since we are dealing with a constant pressure and we're dealing with a constant temperature, I know the temperature goes up when the reaction takes place, but when it comes back to 25 degrees Celsius, then the pressure and temperature are the same for all the gases involved. And if the pressure and temperature are constant, then pressure and temperature don't change during the process. And then, of course, R is always a constant. And so under these conditions, volume and number of moles are directly proportional to each other. So it would be as simple as saying if we have a certain volume of CH4, it's going to produce the same volume of CO2, providing, of course, pressure and temperature are constant. So, for example, if we were asked what volume of O2 is needed, then if we go back to our reaction, and of course here we'll just remember all of these are gases, or at least all but water are gases at 25 degrees Celsius, the volume of O2 needed, well, if the pressure and the temperature are the same, then if we have a 280 milliliter or 0.280 liter bubble of CH4, then that's going to require 2 times as much, or 2 times 0.280 liters, which is 0.560 liters of oxygen to react with it. And of course, if the temperature and pressure are constant. Okay, the last question is, we have a mixture of 2 gases with a total pressure of 10 atmospheres. 40% is gas A, 60% is gas B. What are the partial pressures of each gas, and what are the mole fractions of each gas? Okay, so first of all, what are the partial pressures of each gas? And let's visualize what's going on. So here's a container of our gases, and let's use maybe red for gas A, and we have 1, 2, 3, 4, let's say, molecules of gas A, and let's use green for gas B, and we have 1, 2, 3, 4, 5, 6 molecules of gas B, and that would be a 40%, 60% mixture of the 2 gases respectively. Now, what are the partial pressures of the gases going to be? Well, if the total pressure in this container is 10 atmospheres, and 40% of the gas is gas A, then it probably would make sense that the pressure of gas A would be 40% of the total pressure of 10 atmospheres, which could be written as 0.4 times 10, which is 4 atmospheres. And the pressure of gas B would be 60% of 10 atmospheres, or 0.6 times 10, which would be 6 atmospheres. And that seems pretty logical, and in fact it is exactly what happens. The partial pressure of each gas is the fractional amount of each gas, the percent essentially, but as a fraction of each gas, times the total. Okay, so the next part is, what are the mole fractions of each gas? And mole fraction is what it sounds like. It's the fraction of the whole, that is, in this case, let's say gas A first of all, but we do things on the basis of moles. So for gas A, mole fraction, which we often symbolize by sort of an X-looking thing, it's the Greek letter chi. So the mole fraction of A is the moles of A over the moles total. And in this case, we have pretty simple numbers. It's 4 moles of A out of 10 moles total. And so the mole fraction is 0.40. Which is essentially saying that it's 40% gas A. But we write it as a fraction, and we have to remember we're doing it on the basis of moles. Now, for the mole fraction of gas B, it would be the same thing. The mole fraction of gas B is moles of B over moles total. And moles of B, there are 6 moles of B. Moles total is 10 as before, and this is 0.60, and so mole fraction of B would be 0.60, which essentially means 60%, and again, we remember we're doing it on the basis of moles. Okay, so the summary statement of what we just did, the law is called Dalton's law, and Dalton's law can be written in equation form as the total pressure is equal to the sum of what are called the partial pressures. Pressure of A plus pressure of B plus, if there's a third gas, pressure of C. All of those pressures add up to give you the total. And the pressure of one gas, the partial pressure in this case of gas A, is the mole fraction of A times the total pressure. So it's moles of A divided by moles total. That's the mole fraction of A times the total pressure. And then the same would be true for B, except it would be pressure of B is moles of B times over moles total times pressure total, etc. And so that ratio, moles of particular gas over moles total, is the mole fraction. And that's it for the rest of the Monday, 9th of November handout and class materials.